So our next speaker is Wilson Ricardo da Silva, and he's from the Danish Technological Institute. And the title of his talk is Enabling 3D Concrete Printing Through the Use of Ternary-Blended Binder and Inline Mixing Nozzle.
All right, thanks for the introduction. Good afternoon or morning, everyone, wherever you are in the world these days. And I'm talking from Denmark, sitting in Copenhagen, and I'll talk about the use of ternary-blended binders activated in the nozzle, like as an activating ingredient in the nozzle to enable 3D concrete printing. This is a work carried at the Danish Technological Institute, with me being like the leading researcher on this project, together with my colleague Thomas Yule Anderson. So I'll depart a bit on like the deep science. So I'll try to be as pragmatic as possible, because my goal here is to present like how continuous concrete processing can be done and what kind of strategies can be used to enable 3D concrete printing. So, okay. So the theme, we'll be talking within the realm of continuous concrete processing, and the goal here is like how to use, which methods we can use through the use of continuous concrete processing, which methods we can use to enable structural buildup at the nozzle, at the exact extrusion point, in order to perform a suitable, robust 3D concrete printing process. And the contents of the presentation, I'll go quickly through materials and methods that we considered, some of the test results prior to the 3D printing initial tests, with the description of the setup in itself, and then some examples that highlight the application of this setup. So the materials that we used, there is no magic in it. They were all off-the-shelf materials available here in Denmark. Elsewhere, they would find equivalent materials. So we're using a standard CEM1. The only detail is as a white cement, limestone filler, fine sand, and then a combo of plasticizer, retard, and viscosity modifying agent. This composes the base mix. And that base mix, which is heavily retarded, is then activated by a slurry that's composed of calcium aluminate cement and water, or a calcium aluminate cement plus calcium sulfate and water to be injected in the nozzle. So the strategy here then is like, I would describe as a 2K component. So I have two systems that have to be added at a given rate in order to enable different scenarios that I'm showing the graph at the bottom here. Let me see if I can put my pointer. Showing this chart at the bottom, like how can you modulate the evolution of strength and rigidity, so structural buildup in general, how can you modulate that by playing with these two ingredients? Of course, from the base mix, we can already modulate the open time of the mix by increasing amount of retardant, and also guarantee that you don't have a high workability loss. And then the slope of the curve, like going up, that's when the slurry, the activating ingredient, comes in. When it comes in to wake up the system and enable stacking the layers. And then in terms of mix design, these materials were combined based on the numbers you see on the screen. So basically we have a water binder ratio of 0.39. And here I'm just considering even the full limestone as a binder. So just so you're informed of that. The retarded dosage was fixed at 0.25% by weight of cement. And then the other two admixtures, plasticizer VMA at 0.1%. And then the CAC slurry, or calcium aluminate cement and calcium sulfate slurry, has the same water binder ratio than the initial mix, because the idea is that we don't want to disturb the initial rheological properties of the mix at the extrusion point. So basically there should be, I would say, relatively zero effect at the injection point. We want to avoid some clogging, which is typical of when you're playing with much faster accelerating methods, like the use of shotcrete accelerator, for example. And then we tested this base composition activated with different slurries, again, pure CAC, and then CAC and calcium sulfate at different dosages, in order to identify, okay, map the curve of evolution of structural buildup over time, and then pick one of the mixes as a candidate for printing. So how did we map this evolution of structural buildup at very early age? And that becomes the tricky part. We're using oscillatory rheometry. And then later, for the evolution of strength, there was compressive strength tests just to guarantee some eventual shortcomings that could be from using pure calcium aluminate cement as a slurry. So I'll come to details in the coming slides. But I highlighted the oscillatory rheometry aspect here, and because we're doing a time scan, so we are basically mapping G prime, and phase angle over time using a vane geometry. We have a relatively stiff mix from the start, as you see in some of the printing videos, and we fixed the strains up to at 0.1% because we identified, prior doing all these tests, we identified that the linear viscoelastic regime of the material would be up to 0.2 or 0.3% on a different publication. So this test was mapping evolution of, let's say, altogether structural buildup in simple terms over the course of 60 minutes. And then we get information like evolution of storage modules, loss modules, phase angle, as I mentioned. The yield stress can be estimated, and I'm very happy to see like Reza's presentation. Like the first presenter was showing some of the relationships between how you could get like storage modules with E modulus and then some indications of yield stress. And on a more pragmatic way, you could also deduce the value or the evolution of yield stress using penetration tests, which is a much cheaper and much easier tool to use, but then you only have like isolated measurements. The advantage of oscillatory rheometry here is that we can map the evolution of important properties of rheological properties over time. And the compressive strength test was for the standardized like compressive strength test for mortar samples. And then once again, not once again, but I'm calling everything concrete here, but we are all aware, I mean, this audience is very special. So this audience knows that this is a mortar, but the same could be replicated with a concrete. Of course, there is a limitation on particle size and what the geometry would be and which test method would be done. But it's just for the sake of information, this is a mortar or a microconcrete, as some would say. So here's a typical curve. And I won't go through a ton of the results we got. I just want to highlight like what is the effect, and only on G prime now, there's a lot more data and this could be shared on different publications. So I want to highlight what happens when we are adding this and then slurry as an activating ingredient. The bottom curve is the one with pure white Portland cement. I'm just putting as OPC here. So I have an evolution of G prime over time. And then when we go increasing the dosage of calcium aluminate cement in the system, you have a heavy formation of precipitation of ettringite, and that enables the material to have a higher slope in the structural buildup, and of course a higher elastic contribution, a higher G value over the first 10 minutes. So the order of magnitude in the gain of G prime for the mix activated with 14% of calcium aluminate cement by weight of cement, sorry, it's about 4 times. So that means that within 10 minutes you have a substantial gain on G prime. Within the first minute there is about 3 times. But the advantage is the system is, if I compare this data with a shotcrete accelerator, for example, I would have a much steeper slope of the evolution of G prime, even for the first minute, which could impose, or not could, it does impose some problems on handling and safety of a mixing nozzle. So before I go into details of the mixing nozzle and the printing setup, there is just one aspect to highlight in terms of the hydration system on binary systems and ternary systems. Even though we were aware of that, of course, we still did the test using binary systems with OPC and CAC, and ternary systems with the 3 elements, I mean, adding the calcium sulfate. The problem with a binary system is that we can suffer from a flash setting effect that can block hydration of C3S on the long term. So if you provide enough calcium sulfate into the system that you prevent the flash setting effect, And then the surplus of calcium sulfate will enable both the formation of the structuring entering guide in the system, plus guarantee that C3S can hydrate as it should. So we are not poisoning the system. That means we guarantee there's a fast setting together with a proper or rapid hardening of the material. So, and that's why I mentioned like the compressive strength tests were very marginal on this research here, but it's just to pinpoint that while if we look only at early age performance, which would be the most interesting part if you're doing a print, and then the print will be in the course of like 30 minutes maximum. The compressive strength test results would show that, okay, my mix, which is a combination of the reference mix added with a slurry with 10% calcium aluminate cement, has a substantial higher compressive strength over the course of first 3 hours compared to the mix that has both calcium aluminate cement and calcium sulfate due to that flash setting effect I mentioned. So you can clearly see that like already in the first half an hour and then it continues. But then if you look at long term, like after 3 hours and on to 7 days, then the mix is activated with the combination of calcium aluminate cement and calcium sulfate will have a much higher compressive strength, which is what we want in the end. So we have to guarantee that this mix will not be poisoned. And then again, look at the red bars, the middle ones, where the mix with calcium aluminate cement basically gets stuck at 20 megapascal. Whereas the other mix is both the reference that has no additions whatsoever, but it's not fit for printing because there's no structural buildup necessary to prevent buckling or plastic failure of the material. So both these mixes are like, I would say, like they pass their necessary performance on the long term. Now coming into like how we put it all the science together into some not so fancy mixing process, but effective mixing process and very compact. So the setup we have like two pumping systems, one handling the mortar fraction of it, and then one handling the cock slurry. And the cock slurry, as you see in the photo at the top, it's always being agitated because it tends to segregate a bit. So if any of you attending this presentation is thinking about replicating such a system, that's just a hint that they should be agitated because some segregation that would be could lead into a problem. And how do these two pumps come together? They come together at a nozzle. So I have like a mixing shaft it's about 25 centimeters long, and which means for the normal pumping rates, we have the mixing time like within this chamber from the injection point that's here up to the extrusion point all the way down, it's about 15 seconds. Of course, it would depend on the flow rates you're operating with, but it's for the numbers like we work on, it's about 15 seconds. So with that system, what we have to take into account as input parameters and how to design something that could be printable or could be printed, would be, of course, information from the process. That means what's the travel speed I want to operate the nozzle. And with that, I have to tune what's the mortar flow rate. So I have the extrusion bead, the shape of the extrusion, the extruded material should be something that is, it should be fit to what I need if I want a wider or less wide print. And also the slurry flow rate. So they have to be matched in order to guarantee I have the right amount of calcium aluminate cement and calcium sulfate slurry to activate my system. And then there is information, of course, from the design side. So depending on which geometry and the speeds I'm printing, what's the vertical buildup rate I'll be operating with. And that vertical buildup rate will point back into which structural buildup we need for the material. That comes to the last part. So in that one, I have a base mix design, or we have a base mix design with which is heavily retarded, and then the I call accelerated dosage, but it'll be activating ingredient dosage because it's not a shotcrete accelerator, as most people would associate when they read the word accelerator. It's the slurry with, again, CAC and calcium sulfate. And then we did our first test, and I think it's the first time I'm showing this video. I was a bit embarrassed when it happened, but I think it's fun to watch, or probably rewatch. It failed, but it failed all the way up. This is a column with 1.8 meters in height. we're printing at a vertical build-up rate at 1.6 meters per hour, and it was one of the mixes we tested in the lab with the rheometer. Composed is a binder system, ternary binder system composed of 85% OPC, 10% CAC, and 5% calcium sulfate. So it is a beautiful collapse. Like, it was quite loud. Unfortunately, you cannot feel the vibration or the sound when this happened in the lab. But the interesting part is that right on, when we look into what was going on in the layers, it was actually very clear now. It looks like I don't know, soft ice of like vanilla and strawberry, if you like that, if it's warm while you're watching. There was a poor mixing of the two ingredients. So, and what I have to point is that we deliberately made a slurry. The slurry we were injecting into the system was mixed with red pigment, so we could identify whether there is some mixing of a white base mortar together with a slurry that had the pigment. And you see, like, for architecture applications, I don't have to go too much into details here, but the first few layers, we didn't add any pigment, and then later on we had some pigment. So we identified that problem with the inline mixing test, and then we ran a few more experiments varying motor mixing speed and what's the flow rates that we're injecting. And we could accomplish with by tuning the system a bit and changing the mixing shaft, we could have an improved mixing. So we guaranteed and say that one is checked. So, and then we went on to the same twist column design with the same parameters, added some green pigments for different reasons, and then the result was a column with first we did validate the mixing quality again, and we could perform the same print at the same given speed, and everything was solved. So the problem was not with the mix, it was the process of mixing them two. And then likewise, we reduced a bit now the vertical build-up rate, and I'm already in the application sections. Came up with some different ideas of how to test. Like, we wanted to test which kind of overhangs the material could or could not take. Plus, there are some other architectural aspects. I don't have to go into details here, but we could perform now at a 1.2 meters per hour, the same, we could accomplish a successful print. I said we went down to 1.2. We identified that anything above 1.7 meters per hour would mean the failure of a mix that has this amount of calcium aluminate cement and calcium sulfate as an activation. Before I conclude, there is just one aspect I'm saying, like, I'm talking about activation strategy as CAC and calcium sulfate slurry. That's not the only one. There is also, you can use shotcrete accelerators, but then you will see like the changes in rheology at the moment, like my colleague Thomas is opening the injection of the shotcrete accelerator. Within a few seconds, you see the change of the shape of these drops. It's a good indicator of what's the yield stress of your material. And then within 20 some seconds, you see the change of this shape, these drops being extremely little, and then they will be elongating over time, because then the accelerators is acting, and that's when we are ready to print. Just to show that there are several strategies you can use for accelerating a mix, so that's not the only one. So my takeaway message, material-wise, rheology and hydration control are key to enable to modulate structural buildup and then enable successful printing, but we should also look into continuous concrete processing methods to guarantee that the mixing at the nozzle will deliver exactly what you're testing when you're in the lab. So the results of this research here are just part of a much larger project that went just into focusing more on the hydration part and characterization, but there is some work going on in how to connect all this data from the characterization to material models and simulate the process so we don't have to run a million tests. With that, I would like to thank you for your attention. So if you have any questions, just hit me, or you're welcome to send me an email when you had time to go process what you've heard over the past 17 minutes, I hope.
Okay, all set. We thank you very much, Wilson. That was very nice. We have some questions. why the calcium aluminate cement was injected in the nozzle, and why both retarders and the calcium aluminate cements were used at the same time.
It was activated in the nozzle as a slurry, so we had to create, as you saw, like back in this slide, there is a compartment where we mix the slurry, and then the slurry is pumped into the nozzle. So the slurry comes in here, and then it's injected at this point. So it is a slurry. And why having a retarder and then an accelerator is that when we mix, we are making a batch mixing process. So I mix like 90 liters of mortar, and then I want that mortar to be as fresh as possible for the course of an hour or more, depending on what I'm printing. So I want to have a sleeping mortar, which only wakes up when it hits the nozzle. Everything that happens before it should be sleeping, or it should be on its dormant period the whole time.
Okay. The other question, what family of super plasticizers was used?
There was off the shelf again, PCE. It was a polycarboxylate plasticizer on that one.
Okay. The next question, what type of calcium sulfate did you use? Anhydrate?
It was anhydrate, yes. There are a few, but it was anhydrate.
Okay.
At a 1:2 or 2:1. There's for each part of calcium aluminate cement, we had a half of calcium sulfate.
Okay. And the next question, it can be seen that the compressive strength at 7-day increases when you compare your ternary, or was it the binary binder system, respect for your reference. Did you compare their drying shrinkage too?
We did not do drying shrinkage tests, unfortunately. We're more interested in just showcase the effect of the poisoning that the pure calcium aluminate cement can have or has in the system. But yes, if you look at 7 days, the Ternary-Blended system had a higher compressive strength than the reference one.
Okay. The next question, the test structure in the presentation collapsed due to the slow setting of the mortar. There could be problems with printing tall structures or members. How are you going to overcome this?
It was, I wouldn't say it was a slow setting. Like as you see, like the failure is not a slow setting of the material, but if you observe the failure, it's almost like a ceramic material. It's a hard plate coming down. The material is not flowing. It's a buckling effect. And I would say more than buckling, because there's so much overhang. And if you look deep into the design of the structure, there's some like, there's errors with, we didn't calculate the shear stresses on that geometry, but it was like that whole piece was just kind of cut off because it was just hanging free as a cantilevering beam. So no, it was not a plastic failure. It was more on the elastic side of things.
Okay, one final question. Can we use this inline mixing nozzle to print fiber reinforced cementitious composites?
Not as is. Well, you could, but I would say I could not share, unfortunately, the details of the mixing blades. But if you modify the mixing blades, and depending on which fiber length you're talking about and which volume of fibers you're talking about, yes. But I tend to go away from fibers at the moment because it becomes priority number 2. I mean, I would just be adding more complications to the system. So with a few adjustments, yes.
All right, very good. So I think that's it. Let's thank our speaker again.